Okay, so now let's go. So what is smoke detector or smoke alarm? I think almost all the building, especially commercial building, has this kind of smoke detector. And then the question is how and what's the importance of this kind of smoke detector? Of course, I can see still every year we still have many building got some fire, and then many people die, right, due to this kind of fire in a building. So that the question is how we can use this kind of sensor to enhance this kind of safety and minimize this kind of fire. Okay, so this is still one of the big issues. And then so that again you can see, I think still no matter where you are, so that in Hong Kong, in China, in United States, this kind of fire is still very common. And here there is some estimation about a typical issue. You can see even in United States, they say average every year you about average more than 3,000 structure fire, and then 5 people die, and 50 people got injury, and then you have about 127.8 million property damage. So this is still a big issue. Okay, and then so the question is how we minimize problem. So of course, smoke detector actually has been I think put in some of the government's building code in United States. I believe in Hong Kong, EMSD also has this kind of requirement, right? For many of these commercial buildings, it's required to have this smoke detector. So the key thing here is how we try to find some way for detection of this kind of fire, right? So that here, typically people want to know is what's the important thing, how we can induce fire. So typically here, there's 3 important elements. One is fuel. Now, second one, oxygen. And number 3 with the ignition source, right? So that if you only have one, and then the other is missing, so most likely you cannot induce this kind of fire, right? So that here, now we should talk about it more in detailed information, right? So that means how we look at the development of this fire, and then from the beginning to become bigger and bigger, and then so that in the beginning, if you have some sensor detect that small fire, and then you try to do some control, that is the best solution, right? If you wait until fire reach some critical condition, and especially flashover condition, and then it may be too late and very difficult, right? And really, most likely people will die. So here I show you people how we can try to restudy this kind of fire. They actually have some industrial standard. They use a kind of cone calorimeter, and then try to measure the heat release rate or heat flux. Okay, so that in this case, we can carefully study about for different material in a building, what's typical HRR. So here I show you this is typical machine to measure this kind of HRR. Okay. And they also try to use different material, common material in the building, and try to study about this kind of HRR. So here's the typical result. Based on this experiment result, I think in the literature, so people find typical material in a building, carpet, and chair, paper, and other things. So typical heat flux. Now see, this is based on this particular machine, you can measure this kind of HRR, why heat release rate. So that you see, it really depends on material. Some material, the basket has much higher, and also the letter tray is also very dangerous. Okay, and here actually they have done some experiment to understand about fire from this chair. And if you have more understanding about this kind of how the fire will grow, right? And then most likely we have a more idea about how we can do this kind of detection of fire or small detector. So here they have this kind of a time-dependent measurement result, all right, based on this machine HRR as function of the time. You see, so you see if we can look at this dynamic behavior of this heat flux as function of this time, and then most likely heat flux will actually is a heat generation, so that it's related. That means you probably can think about some way to do detection of this kind of fire. Okay, so anyway, so here they also try to do different kind of experiment and then try to look at a typical time-dependent heat flux at functional time. And here now, let me show you. Once you have a base understanding about this kind of fire, like kinetics, right? And then see, here we talk about smoke detector. So the first detector was developed in 1970, and then later on in 1977, NIST has conducted this kind of smoke detector testing, and gradually more and more, you see, about 10 years from the invention of first battery detector, and then so that more and more home will install this kind of smoke detector. So in the United States, they say, okay, maybe in year 2008, about 96% of home will have this kind of smoke detector. Okay. So again, so what's a typical way how we can detect this kind of fire or smoke detector? So typically, they have two dominant methods. One is ionization method. Second one is a photoelectric method. Ionization means there's some very small amount of this kind of radioactive material, and then they will conduct electrical like a behavior, right? So that in this case, once you have some fire or some smoke, right, go through here, and then they will trigger some electrical current. In this case, if you're able to measure this kind of electrical output, then most likely we can use it as smoke detector. The second one is a photoelectric sensor. So that the idea actually is simple. That means once a smoke from fire, and then this kind of photo cell, we already mentioned this kind of light sensor, of course, in our Arduino and our previous lecture. So that means once you have a light, some maybe LED, right, illuminate this kind of your chamber, and then once your smoke enter this kind of chamber, so that you can change the optical property, right, and there's some additional sensor, right, light sensor to detect that kind of optical change, right, and then relate to the input smoke concentration. So this is a typical way. There's two dominant way people try to think about the smoke detector. So here I show you how about this comparison about these two different methods. In general, ionization alarm is more sensitive to small particle of combustion, cannot be seen or smelled. And then, so but for photoelectric alarm, I will be more sensitive to large particle of combustion emitted by this fire. So here I show you the first example is about how we use the photoelectric method as small detector. The idea, as I show you, first is a light source, and then goes to after lens, and then you have this kind of photo cell, a light sensor, right? And then once you small enter this kind of particle, this kind of zone, and then you can change optical property, right? And then use optical sensor or photoelectric cell to detect this kind of like optical property change related to input the small particle, right? So this is the basic idea. And of course, in reality, they have a much better optical design, right? A farm light source, and then you have some special chamber, and then you have a light sensor, and then you have some small particle. We call that kind of optical, I think, scattering effect. So in this case, light sensor will pick up this signal and then convert light into output voltage. So this is basic principle. We can try to make this kind of photoelectric small detector. And then, of course, how we try to look at this in photoelectric sensor. In general, this best as a detection slow smoldering fire. Like you can see the furniture ignite from secondary. And then it can detect the compartment, some particle from this kind of fire. And the particle size is about 0.3 to 10 micron. And of course, it may also sensitive to the light smoke. And also, it's not very sensitive to steam. So in this case, it will be useful and better used in near the kitchen or bathroom. And in general, this kind of photoelectric sensor will have higher power requirement than ionization type of sensor. So here, let's show you some basic principle. Typically, we have LED, and then it illuminate, right? It applies some voltage on LED. We already mentioned LED in previous lectures, right? And also Arduino has also kit LED, right? But this particular one is we need have what? LED generate infrared light in the detection chamber. And then, so in this case, if the small particle exists in that chamber, and then it causes some scattering, light scattering effect. In this case, it can reduce the amount that reach this kind of optical sensor or detector. Right? In this case, I can try to look at this kind of optical light intensity change to relate to this kind of input concentration of this kind of particle. So this is the basic how we can try to do this kind of detection. Right? If you reach some threshold value, and then probably it can trigger this alarm, right? Again, alarm we can also use piezoelectric buzzer in our Arduino kit to induce this kind of the sound, right? So that's basically so this kind of small detector consists with what? First is transducer, light source, and then we have a optical sensor, right? And then for optical sensor, we convert this kind of optical input to electric output. And then once it reaches a threshold condition, and then if particle has caused a lot of light scattering, and then we may now reach threshold voltage, and then you can trigger this alarm. So this is the basic idea about how the photoelectric sensor work for small detector. And then of course here I show you some the real schematic design of a photoelectric small detector. Again, the key thing here is you have infrared LED, number 5 here, and then the second thing is you have sensor, photodiode or some light photocell, a light detector, and then there's some optical chamber, and then so of course this has some special design. Make sure you can really have a very sensitive to detection a very small amount of this particle, right, from this kind of fire. And then here I show you some the photograph of these photoelectric small detectors. So you in general is you need have not only the LED photodiode or light sensor, and also you have some additional piezoelectric buzzer, right, to generate some sound. And for more professional small detector, you probably need additional IC. So here I show you how we use this kind of typical IC in the small detector. So one common IC, low cost IC is A5366. Okay, it's low code by CMOS circuit, and then in this case, it be used for this kind of photoelectric small detector, right? And that means in this case, we use this IC to connect with our LED, right? And also connect to our the sensor, the photo cell or optical sensor. Okay, so this particular IC actually is not too expensive. If you look at Alibaba Taobao, I think it's about 5 to 6 RMB. Okay, if you want to look at more detailed information, you may also look at the data sheet here. So you try to go here and you can find the data sheet of this particular IC for real application. So basically it's a photoelectric smoke detector with interconnect and timer, okay? So again, in reality, you need to have, again, LED, right? And photocell, light sensor, and the other piezoelectric buzzer, okay? So actually, your Arduino key do have this kind of piezoelectric buzzer, right, to generate sound, okay? So let's look at some real application. So again, so this is a brief introduction about photoelectric smoke detector. Now we have a second one is ionization, this kind of a sensor, right, for smoke detector. The idea is, again, you have some special type of radio active source, and then so in the chamber, if you have you analyze this kind of air, right? If you have some small particle exist, in this case, you can generate some additional output current, so that in this case, if you can detect the change of output current, and then you can relate to input the concentration of small particle. Once you reach some critical threshold the value, then you can trigger this kind of piezoelectric buzzer to generate sound, right? So that is the basic idea of this ionization smoke detector. In reality, here you see in more detailed schematic design, you have battery, and then you have this kind of radiation from this kind of very small radioactive material, and then once your small particle is here, and then you cause this additional ionization and really change this kind of output current, electric current, right? So this is a basic idea how ionization smoke detector work. So that again, typically we use a weak radiation source. For example, this Americium 241 is some kind of special kind of radiation source. Of course, this amount is very small. You will not cause some problem for human body thing, right? If you have very strong like nuclear active material, of course, probably you can cause some health concern. But actually, this amount is very small. It's about 0.28 microG. Okay, so for ionized air, you can conduct some electric current. Okay, and then in this case, you detect the circuit with sense this kind of current. Right? If you have some small particle, and then you can actually cause some change about output current, electric current. Right? So if current is reduced, and then to some threshold, and then you along with sound. So this is the basic idea of how ionization sensor work for this kind of small detector. And here I show you one of a product of this ionization smoke detector. Okay, so inside again you have basic ionization like material, and then you have piezoelectric buzzer, and then of course your ionization chamber, and you have a white and round thing, and then it's a piezoelectric buzzer, and with additional battery. So here is look at the side view of this type of smoke detectors. Again, the casing here is you have ionization source, and then you have some chamber, right? Your chamber, and then one smoke particle enter the chamber, and then of course in this case you can change the output current. So in this case, if the current is reach some critical condition, and then you trigger this alarm. So this is the basic idea about the smoke detector. Okay. So here in general, ionization sensor will be is good at the detection fast alarm flaming fire, like grease fire, and detection combustion particle size range from 0.01 to 3 micron. Okay. Again, typical hair size is about close 90 to 100 micron. Okay, so this kind of ionization sensor is more sensitive to dark and black smoke. And unfortunately, this ionization sensor is sensitive steam, so that it's probably not good to install in the kitchen, also bathroom. Okay, so that you see that means we have two type of small detector, so that so you need, when you try to use now this kind of to buy this sensor to install in the building, you need to be careful, right, to pick up the right type of a small detector. And here I show you, of course, nowadays you can find some better type of the small detector. For example, this is a new type of small detector which consists of photoelectric plus additional CO sensor, carbon monoxide sensor. You say, so that sometimes if you want to look at the more detailed fire output, right? Fire can cause some smoke and also can also generate CO2 and CO, right? So that so this particular design product made by this kitty company in the United States, they use two type of the sensor way to enhance the performance of this small detection. Okay, of course, for combination alarm, typically, most likely you can have, I think, minimize the false alarm and also increase the reliability of this kind of small detector. And so that is very common now. And so of course, typically, how we power this kind of small detector, there are two ways. One is AC powered small detector, and the second one is battery powered. So battery usually use a 9-volt battery. And for AC power, so that in this case, of course, in this case, you can small detector can last for a long time without replacing the battery. Okay, and at this moment, if you can use this one, and I think probably it can minimize the kind of maintenance effect. And for second one is battery power. So in this case, you need to have regular maintenance and check, make sure the battery is still okay, and then you only may need to replace this kind of battery on a regular basis. Okay, here is additional flame detector. It show you for this fire safety sensor, right? So we have first is look at the optical sensor. The second thing, ionization sensor. And then we have a combination of more than one type of sensor, right? Photoelectric and plus maybe gas sensor. So flame detector also have some different way, right? So that I think in Arduino kit, we also have some the flame detector sensor. Okay. Flame detector, how we detect flame. So here, actually they have a typical way. We can use either UV detector. In Arduino kit, we do have a UV sensor. And also second one is you may use NIR, near infrared flame detector. And or you use IR flame detectors. So I think it really depends on, I think, different kind of this optical of this flame detector, different property. Okay. So of course, here they show you the development of this small detector in the past many decades. So gradually, people gradually improve the performance and reliability of this small detector, starting from 1943. Gradually, you see they try to improve the optic design, backward scattering, and then also try to minimize the false alarm, and then gradually also combination of more than one type of sensor to increase the reliability of this kind of small detector. And of course, nowadays people gradually think about some of the new type of smart sensor or smart small detector. So this is the I think one product made by the company because the new road smart small detector. So basically, for all this kind of a smart sensor or smart detector, most likely they have multiple sensor, more than one type sensor, and additional sensor algorithm, right, to improve reliability and minimize false alarm. So this is something become more and more common now. Okay, and so here I show you one new type of a smart small detector made by Siemens in Germany. So again, the key thing here, there are two IR light source. So that this is a photoelectric type, and then your sampling chamber, right? And then you these two IR source detect both forward and backward light scattering, and then you have a more sophisticated optical design, so to prevent wrong light reflection, and also they have two temperature sensor and one CO sensor. So this is a much more sophisticated compared with the one which I mentioned in the previous slide. Okay. And of course, so why you call this kind of new role small detector? Because it's not only just simple sensor, right? Multiple sensor, but with additional the program, right? Signal processing program. So that means in this case, you can improve again reliability and also minimize the false alarm. And so this become, I think, more and more important, right? You want to have increased reliability and minimize false alarm. And then, so in this case, you may want to look at this kind of new type of small detectors. Okay, so here you can see they have a quite sophisticated the signal processing program to look at the fire risk and also false alarm, and look at geometry and the other issue, right? So that and also you look at the issue risk to the person. Okay, so anyway, I think we already this is briefly described about small detector. Again, so small detector, I think it's very important in many commercial building. So that I'm very sure the EMSD in Hong Kong government require, right, this kind of all the small commercial building to have a small detector, right? So that to make sure that they meet this kind of building code. And of course, here I show you about the in the past many decades, what's the typical issue for this fire death, right? So that in the past, from 1950, so that you see, if we have more and more better and better small detector, and then in this case, you can see you can really minimize this kind of death due to this fire. Okay. And so in the past several decades, so gradually, I think the number of deaths, right, per 1,000 fire is around 8. Okay. So they also, I think this is data from the US NFPA, so that in the past many decades, so gradually, I think because the requirement of this kind of small detector, so I think this kind of death due to the fire, I think gradually reduced. But still, you can see you cannot reduce to 0. So the question is, how can you think about to improve this kind of smart building with additional sensor and to make sure that minimize this kind of fire problem? I think still important issue. Okay, so I think we almost run. See, I don't know. Do you have any question for this particular photo cell? Of course, I will not talk about all the detail, but also try to think about can you use Arduino to make this kind of small detector? What do you think? It's possible you can look at this kind of Arduino-based small detectors. Let me check. Actually, Arduino do have the some way to make an Arduino-based smart detector. So that here I show you how you can use Arduino kit to make this kind of Arduino-based small detector. Basically, you use the Arduino MCU, right? And then you have a 10 kilo ohm potentiometer, and then you have MQ6, actually or MQ2 gas sensor, and toggle switch, and 330 resistor, LED, battery, and also some DC voltage step up the module. Okay, so that then you can. The key thing here is we need to use right sensor, right, to detect the smoke. Previously, we show you we have either using photoelectric sensor, right, LED or ionization. But this particular one is use the kind of gas sensor, right? Gas sensor, that means if a fire, you generate some kind of gas, right? And then if you have a right type of gas sensor, in this case, it's possible you can use for this kind of Arduino-based smoke detector. Here I show you about this Arduino compatible MQ6 gas sensor. Basically, it's a resist type of semiconductor gas sensor, and then it can detect this kind of LPG and some of this kind of a typical combustion gas, and then so typically you see the sensing resistance range from 2 kilo ohm to 20 kilo ohm in about 2000 ppm, this kind of gas. So here this is a typical information about the sensitivity of this gas sensor. So that so X is ppm, part per million, from 100 to 10,000 ppm, right? And then Y is a normalized resistance, and respect to the original resistance. So it's a normalized. You can see it really depends on what kind of gas, LPG, and then C4, CO, so then there are different kind of response. And typically for most of this kind of gas sensor, actually, unfortunately, what's the problem? Most of the kind of gas sensor is not only sensitive to one type of gas, it's also sensitive to multiple gases, so that we need to think about not only sensitivity, but also what? Specificity. Specificity become also quite important. Let me see. Specificity. That means how I can now make sure our gas sensor can be sensitive to one particular gas, right, for our application. So this has become very critical for more reliable this kind of sensor. Let's see. Let me put down some key here. So for all kinds of gas sensor, or specificity is the second important key performance parameter. Right. The first thing is sensitivity, right, and specificity is a second important thing we need to consider. Then once you have this base idea, next one is how can we make this Arduino-based smoke detector example. Basically, you MQ6 or this MQ2, you need to have what? Provide some power now to heat up this kind of sensing element, right? This is semiconductor gas sensor, right? Heat up to certain temperature, and then output is a resistor. So that in this case, you need to connect into some kind of a reference resistor, and then in this case, you can based on change resistance, and then you can try to create some threshold voltage, right? If you reach a critical voltage, and then you can try to turn on LED, and then also you can also try to generate this kind of output voltage, right, for the piezoelectric buzzer and generate some sound. So this is a typical idea how we can make this Arduino-based smoke detector. I remember we have a one project look at this kind of gas sensor in the town gas that product, right? So that you may want to look at this kind of a reference design for your project. Of course, you may also look at this kind of the YouTube, and then try to think about how they can really make this kind of example. Let me look at this example.
Welcome to the Z-Hub's Mad Scientist. I'm Professor Z, and today we're going to attempt to take over the world using Arduinos. Grab your favorite Arduino board and put on your tinfoil hat, because it's time to build. Today, we will be attempting to take over the world by building a gas leak detector gun. And also, if you're not using this for detecting gas leaks, you can also use it as a prop ray gun for a Halloween costume. The main component of this is one of these HKUST gas sensors, and these detect methane, propane, natural gas, pretty much any flammable gas that you would be using around your home. And I just simply have it set up with the sensor here on the end of the tube, and I have a power button, battery pack, and then I just have an old analog meter here that detects the strength of the gas. So the closer you get to the gas source, the higher the reading of the meter will be. And then there's also a potentiometer here, and this is to tune the detection strength of the meter, so that as you get closer to the leak, you can increase the sensitivity, so you can narrow this in right to where the leak is. Let me grab here. I'm going to demonstrate it working. Turn it on. As you can see, I also put an LED backlight on the meter. Now, I had already calibrated it, but it does take a few moments to warm up before it will start detecting. It's not quite warmed up yet. As you can see, when I do put butane gas underneath, the meter does go up and down. And it generally, I think it takes about a minute for it to warm up. And then it's at its most accurate. As you can see, you gotta get about, once you get about an inch away from it, it'll peg the meter. But that's where this comes in. You can have the sensitivity decrease, and then once you get close to it, you can use this to increase the sensitivity so the meter doesn't move as quickly. And then you can zero in on the gas leak. All right, let's take a look at the construction of it. And then what we'll do is we'll go over and take a look at the sketch for it. So, well, first, it pretty much does look like something from one of the old black and white Flash Gordon sci-fi shows, a ray gun. And what it is just PVC pipe. This is, I think this is 1-inch pipe. We have a angled, it's not an, I think that's a 45 degree. I think that's what that would be. And then for the front, I have a reducer on here down. I do believe this is 1/2-inch pipe. Let me grab my ruler, I can check real quick. Actually, no, I think that's 3/4 inch. But the pipe I used is when you cut the slit in the middle in half, it fits across lengthwise perfectly. Now you can also get these not on these boards, and it just happened this is the particular ones I had here on the boards. But I'm using the analog reading on it, but not the digital, so you don't really need this board. But if you got one of these, you could desolder it or just get the HKUST sensor without being on the board, and you could glue that right to the front of this. And it would look a lot nicer, a little bit neater. But this is what I had on hand. This is what I used. I did order one of these. It's not on one of these boards, but it'll be a good month before that comes in the mail. Sorry, then this body itself. This is called a conduit body. You'll find this in the electrical section of your hardware store, home improvement store. And they come in many different sizes. Just go with one that's just big enough to put all your stuff in. This again is one that I had on hand. I could have probably went with something just slightly smaller, but I had it on hand. And these aren't that expensive. I think this was like $3.99. So very inexpensive project enclosure, and it works perfect for this. Works absolutely perfect. So I'm gonna go ahead and remove the handle, make it a little easier to see things here. So on the bottom, I have a little AA battery holder. It holds 2 batteries, and it has prongs that come out. I just drilled 2 holes, so these run through to the inside. Then I use super glue and super glue to hold it on. It should stay permanently. Super glue holds pretty good. And yes, I am powering this with only 3 volts, but it is a 5-volt Pro Mini we're using on the inside. We'll get to that in a moment here when I open it up. Then on the top, once again, we have a potentiometer. You're going to want a 10K. For this, it does matter if when you're doing analog reads off a potentiometer to your Arduino board, the value really doesn't matter, but we're not using this as an analog read to the board. We have it tied to the meter, from the output to the meter. So we're controlling that, and I found 10K works the best. I'm pretty much going to say you're going to want to stick with the 10K, otherwise you're not going to have much sensitivity control. It'll be too much or too little. You can try, but then I have simply an on and off power switch. And then I have an old analog meter. You can order these online. This one, I don't know, this came out of an old junk CD radio, stereo, something. When I find junk electronics garage sales, I always take them because there's lots of parts like this you can rob out of them. All right, with that, let's open it up and we'll take a look at the inside. That's the wiring on the inside. Now, down here in the corner, because we're using 3 volts and we need to power the Arduino at 5 volts, we're using the voltage power step-up converter. And this is the exact one that's in there. It's right here. It's adjustable. This is a MT3608. You can get these on eBay. I think they're like just a little over $1. It's shipped, and it is adjustable. This little multi-current potentiometer here. You put your voltage in, then you got your voltage out. You put your input, what you're going to be running. And you use this to set voltage at 5 volts. And until those batteries go below the minimum voltage this needs to work, which I do believe is 1.5 volts, it will constantly keep it at 5 volts. As the batteries decrease, this won't go down to 5 volts. It will keep it regulated at 5 volts until the power supply voltage drops below what this needs to operate, and it'll just shut off. Means you're not going to be using this a whole lot, most likely having it on all the time. This was the way to go instead of putting multiple batteries in there and then you have to use a step-down converter. So then down here, we have one of these little mini breadboards. I was going to solder it together, but I have a whole bunch of these, and it was the perfect size to fit right in there. It has this peel back stick thing on the back. I just went ahead and used this. That way, if I want to modify anything in the future, in which I am going to be replacing this, like I said, I can just simply unplug something and plug something new in. And as you can see, that's the one I got in there. All right, for the exact circuit on how to assemble this, just look in the description below. You'll find a link to this project's webpage. There'll be a schematic on there, as long as the code that we're going to look at here in just a moment. The only other things to mention, I added a little LED here as a backlight. It's just hooked up to the power. Whenever the power's on, the LED comes on. And then I put a 330 ohm resistor in line in the jumper here. It's underneath the shrink wrap. There is a resistor in there. And then I have tons of these jumper wires. So to keep everything color coded, so I could differentiate between stuff, I just went ahead and used some of my jumper wires because I go through these like crazy. When the old ones, the ends start wearing out from heavy use, this is how I recycle them. They just get permanently soldered into the project. All right, I think we've covered everything. Well, then of course there's the on-off switch here, whatever kind of switch you want to put in there. And to cut everything out, I simply use the Dremel tool with a cut-off blade to cut this notch out for the plastic. And then I used a cordless drill to drill the holes for the power switch, the potentiometer, and the two little holes for the battery pack underneath. I used a real tiny drill bit on the Dremel as well to drill that. All right, I think we went over everything. Once again, in the description below, you'll find a link to the web page. You'll find a schematic on there. Plus, I'll have a parts list. Oh, excuse me there. Plus, there will be a parts list as well. So, all right, I'm going to go ahead and fire up the computer. I'll catch you over there in just a second. We'll take a look at the sketch that we're using to control this. All right, I've got the Arduino IDE opened up here. So what we're doing here first is we're just defining MET, just short for meter. That's our analog meter. That is on digital pin 3. And the void setup, we're just setting the pin mode for that as output. We have a serial begin and a serial print down here. This is for testing when we're first setting this up, because you might need to change just a tiny bit down here. We'll get to that in a moment. In the void loop, we're just doing an analog read of, I've got the gas sensor on analog pin 1. So we're just doing an integer, we call it val for value. Reading that. Then what we're doing is we're constraining that value. We're going to keep that value between 200 is the minimum value and 1000 is the max. I found that just sitting in the room, no gas near it, it would get the reading between 50. As it warmed up, it got more towards 100. I found it works great running it at 200. And when I was putting butane and gas right directly onto it, it was pretty much hitting 1,000, maybe 1,001, 1,002. So I just constrained everything here. You should be okay leaving this alone. Then what I did next is, because we're going to be doing an analog write, we're taking that value and we're mapping it, to a value of 0 to 255. Because that's our analog write value. It has to be between 0 and 255. So we're just mapping that. Now, you can play around with this a little bit. If your meter is smaller and you're way over pegging it, no matter how you're setting your potentiometer, you can drop this value down a little bit, maybe put it at 200, try it there. The constraint up here, most likely you're going to want to leave this alone, but if you do get into some problems where they...
Okay, so here I just quickly give you some example about Arduino, how to use Arduino with gas sensor for smoke detector. Of course, in your Arduino kit, you don't have MQ2, you don't have MQ6 gas sensor, you have MQ2. I believe they are a family of this gas sensor, and probably the sensitivity has a little difference. But in general, you can try to use your Arduino kit's gas sensor as a way to make this kind of smoke detector. Okay, you can, if you want to look at the thing, you can try to look at our Canvas website, and I do upload this Arduino MQ2 gas sensor. Right, that is in your Arduino kit. Okay, so this is I think very similar. NQ2 and NQ6 are very similar. I believe that only have some little difference in terms of some sensitivity and performance. So it's I think quite similar. Okay. Do you have any question for this particular smoke detectors? Because we run out of time, and then I cannot talk about all the detail about this smoke detector. But at least now you have some basic idea how you can really make your own Arduino smoke detector. Do you have any question for this particular part? Any question? Huh? If not, of course, I also find this particular Arduino smoke detector need a MT3608 DC-DC converter chip. Actually, you can buy from Taobao. Actually, it's very cheap. It's about less than 1 RMB. So that this is something really low cost, small detector. You can really make this one by yourself. So you see, I just find from the Alibaba Taobao, it's very cheap. It's only less than 1 RMB. Okay, so that it's DC converter. Okay, DC converter, very cheap. Okay, so do you any question for this particular topic? If not, I think we need to go to the next chapter. So that so next one is we talk about is our gas sensor. Well, gas sensor is another important big family, right? And so this particular one, we're not talking about only gas sensor, but also gas sensor with additional gas analyzer, right? So this is I think quite important. So here I just show you how we use gas sensor. It can use process control industry, and then environmental monitoring in the building, boiler control, fire detection, alcohol breath tester for police, right? Detection of harmful gases in mine, home safety, and grading even for agricultural product like coffee, spices, or even in the future, if this kind of smart gas sensor, maybe you can use to look at what quality control about smart cooking, right? So that is something is possible. Yeah. So here I show you one of the important gas sensor we think about is probably CO2, right? CO2 is important for the building, right? According to I've seen many of the building code, right? Especially HVAC system, you have to control this kind of CO2 concentration in the building, right? I mean, typically for commercial building HVAC, we have a typical this kind of air handling unit provide cold air, right? In each room and classroom office, but at the same time also fresh air. Now provide this thing so that you make sure that you have a good concentration of CO2, right? So that here I show you typical concentration, right? For typical at the very concentration about 350 to 450 ppm, and then acceptable indoor air quality is about 600 to 800 ppm, and then so that the tolerable indoor air quality 1000 ppm, right? And then so the for those dangerous concerns is if you reach 6,000 to 30,000 ppm, then probably it's okay. But if it's too high, 3 to 8%, you have a big problem, headache or something. Okay, so if less than 10% of the CO2 in the building, you may have some problem, vomiting, unconscious. Right? If it's more than 20%, and then most likely you die. So that this CO2 is one of important concentration for the building. So here I show you compare different types of CO2 sensor in terms of performance and the price. You can also get the low cost sensor. The one in your Arduino kit, I believe, is in this kind of range, about low cost, less $10. And then if you want to have high performance of this kind of gas sensor, and then in this case, of course, there's some company, right? Figaro is a company in Japan, GE, Tech, and they're going to have a more performance. And then for some Honeywell, and I see, you see, they have even better and more expensive, right? So it really depends on the requirement, right? So you have different type of this CO2 gas sensor. So here again, I show you what we care. What's the typical gas we care? Right? CO2 is important. CO, carbon monoxide, related to safety and fire detection, and VOC, volatile organic compound, is important for indoor air quality for the building, right? And NOx is important for what? It's important for the building, the engine control in the car, okay? And then CWA is related to, that is the chemical warfare with the homeland security and combustor, right? So of course, well, recently in Hong Kong, we may also think about some gas sensor for tear gas. Right? Do you think police fight a lot of kind of tear gas, and then I believe some of this kind of gas from the tear gas gun probably is not very healthy. So that how to use the right gas sensor to detect this kind of tear gas produced on the police in Hong Kong. I think this maybe have some important issue when you think about. Okay, and so here I show you what's a typical way we try to do gas sensing, right? Again, the simplest way is semiconductor sensor, right? Like a metal oxide semiconductor, okay? So that or you have an electrochemical sensor, or your catalytic sensor, and then another one is optical, NDIR. What is NDIR? It's near infrared. Now, optical sensor detect this kind of gas, right? CO2. Okay. For commercial HVAC, like a building, right? Demand control ventilation. What we know, I think typically the typical thing is NDIR. Okay, but it's quite expensive. I remember it's about $700 for traditional CO2 sensor in the commercial building. Yeah. Here I try to make a more detailed comparison about 4 type gas sensor. Again, you have a semiconductor type, and infrared spectrometer, catalytic combustion sensor, and electrochemical gas sensor. Okay, so semiconductor base is you have some absorption of gas molecule on that material. Your MQ2 or MQ6 gas sensor in Arduino kit is this kind of semiconductor gas sensor, right? And good thing here is advantage is high sensitivity and low concentration and long life and good reliability. Okay, and then you have a catalytic sensor, combustion sensor, so that this is one of all the gas sensor people developed many years ago. And then in general, you have high accuracy at the high concentration and high selectivity. Okay, and then you also have electrochemical gas sensor. You can detect those kind of electromotive force change caused from electrochemical reaction. It's high accuracy at the low and medium concentration rate. Okay. So here I show you about one of early type of gas sensor people developed many years ago. You see, we call it's most common like methane sensor, right? And so look here, basically it's some special type of pallister. This is called the pallister. Pallister means it's a pallet plus resistor invented by British scientist Alan Baker. You see, he have a patent in 1963. So basically, once you have this kind of special kind of pallister, right, and then you have some catalyst, and then you apply more voltage at a high temperature, and then you, in this case, once you have a gas input, so that in this case, the output signal will be different, right? So that if you have a high concentration of this kind of gas, right? For example, this methane, and then it reaches some critical condition, then the sensor output will be high. But if you continue through and then the oxygen deficient, then you will change our output signal. Okay. So the good thing here is it's one of the most mature the kind of sensor developed many years ago. But the good thing, the disadvantage of this kind of gas sensor is high power and also susceptible to poisoning. That means if this gas sensor already attached with this kind of existing gas, and maybe it will change the performance, and then it's become not very reliable, right? The typical lifetime is 3 to 4 years. Yeah. So again, this type of gas sensor, catalytic combustion gas sensor, is already developed by Dr. Oliver Johnson in 1926. You see, it's a long time ago. Right? So why this this guy want to develop this kind of gas sensor? It turns out there's a motivation because at that time, U.S. has this kind of big oil company, and then so that the oil, if those worker work for this oil company, if this worker didn't carefully look at the safety issue, probably some of these gas may cause some like a explosion or cause some problem, fire. Right? So that's why, so that I think the oil company, Standard Oil Company, try to think about how to improve the safety of their industry, right? So that eventually they develop this kinds of catalytic gas sensor. Okay, so that the base principle, I think, very similar to what we have learned before, right? Basically, you have that particular we call pallister. It's a hot wire, catalytic platinum filaments, and then you have a reference this pallister, and then you have this kind of Wheatstone bridge. You apply the voltage, right? And then if you have this kind of active this kind of sensor, right? Active the pallister, they have some exposed with some gas, oxidizing gas or vapor. Then in this case, it can cause increase in temperature of hot wire. This kind of active B, and then you can increase the electrical resistance of this wire. Right? In this case, once a Wheatstone bridge, so that I can detect output voltage related to the change of resistor of this active B. So this is a basic idea. Of course, the second one is the hot wire is reference B, right? So use as reference filament, right? So again, this is one of very mature gas sensor invented many decades ago. Okay, and so the typical lifetime is 3 to 5 years, and you need to calibrate about 3 to 6 months. Okay? A typical temperature of this heater is about 300 to 500 degrees C. Okay, let me see if I can show you the video of this particular pallister. Again, you have two sensing element, reference active one. When you have this kind of gas go into this kind of sensor chamber, you see, then you can some reaction. So in this case, the change resistance, right? So in this case, we can have output, right? So you have Wheatstone bridge, and then you can detect the change resistance into the change of voltage. So this is a basic idea of how this kind of well, I think catalytic gas sensor work. Here I show you almost the first commercial catalytic gas sensor invented in 1926 using two-job method. You see, and then gradually become more I think compact. Model B LEL monitor. LEL means a low explosive limit. Okay, so that the company has already sold about 100 units in this old day, 1927. Yeah. And then gradually also people try to make more and more compact the sensor. Right? You see, from the very big it becomes smaller and smaller. So this is a Model B. They have this kind of sensing element, two filament in the glass tube, and the 1, 2 C as reference element. And then gradually, you see, they also greatly improve the design and the packaging of this kind of gas sensor. right? So this is a JW Model C. You can see compared with the previous one, it become better and better and cheaper. Not cheaper, more compact design. And gradually, people also try to, the other company, NSA, also try to, I think, they try to borrow this kind of gas sensor from JW, this kind of company, and then they try to duplicate this and make their own gas sensor. Okay. So this is the second gas sensor company, and then gradually they also make this kind of Model 2A of this kind of gas sensor, but they don't call the gas sensor. There's some special name like here. And gradually, even in Japan, they also have some researchers try to come with a different type of gas sensor. So this is optical gas sensor using the optical diffraction. It's invented by originally it's Dr. Uzumi Doi. They do the initial research in 1927 in the Institute of Physical and Chemical Research Institute in Japan. And later on, this institute also, Dr. Zero Tsuji, right? They tried to develop the first working prototype of this gas sensor. And again, you see, you also try to develop this kind of gas sensor to prevent explosion, an oil tanker and coal mine. You see, in China, we still sometimes we still see this kind of some problem, accident happen in those mining industry. So that how we can have this kind of low cost, high performance gas sensor to improve the safety, not only in a smart building or this kind of mining industry. I think it's still very important. And of course, gradually they also try to make a more and more compact design. So this is optical, right, gas sensor based on using the principle of light diffraction in air, right? So if this kind of gasoline vapor enter this kind of chamber, then they cause some diffraction, light diffraction, and light diffraction will create some visible fringe line. Then they shift to the indicator gas concentration. So in this case, if you are able to look at this kind of visible fringe line, and then in this case, you can relate to input concentration of the gas, right? So that is a basic way from input concentration to output optical change about this kind of visible fringe lines. This is a optical one type of optical gas sensor, and gradually, I think this it's not company actually, it's a research institute in Japan. They call Yi-Kuen Keiki. I think it's probably the spin-off company from the Yi-Kuen Research Institute from Japan. So that once you make a good prototype, and then they start this kind of company, Yi-Kuen Keiki company, to make this kind of optical gas sensor. And again, gradually, I think there's a more and more type of this kind of gas sensor was made by several companies in US and in Japan. This Yi-Kuen model GX7. You see, gradually they make a more and more compact design. And then in this case, about 12,000 was sold in 1970s. See, the company, they gradually make a better and better. This is gas tech, this kind of more portable gas sensor. Right? You see, in this case, it's a 3 sensor, and then try to improve the performance of this property. And gradually, the company make a better and better and more portable gas sensor, right, for this safety, LEL, and the combustion gas sensing and O2 sensor, and put in this more compact design. So this one will be used for remote to sensor for testing on manhole. We can also make another type of the kind of portable gas sensor. Detect, you see, LEL combustion gas, or detect O2 and S2S. So this is, I think these gases are very common in the industry. And gradually they are making a more and more compact design, right? So this is Yi-Kuen's S82CO, so that a series of this kind of gas sensor module. And gradually they also try to make even more compact design, right, with this kind of multiple gas sensing in this pocket-sized gas sensor module. Okay, this Yi-Kuen, again, you see they're making a better and better design. Eventually, I show you the basic idea of this kind of catalytic gas sensor is you have a pedestal, right, hot wire, and then we have catalyst, and then in this case you have built the Whiston bridge, and you have a reference hot wire, and you have an active this kind of hot wire gas sensor, and then in this case once you get input, then you can change cistern, and then Whiston bridge will what convert data R into data V, right? So this is the way I can make this kind of a gas sensor. Okay, compared with a different type of material to make this kind of gas sensor, typically I think that in early day we use PT, platinum wire, using 20 micron PT, and then people also try to different kind of material, right? So that the response has a little bit different behavior. They also try to look at the different design, right? Again, you pattern this kind of pedestal, right? So it means that you have not only simple one wire, you have a number of winding, the turns, right? The number of turns will be what? If you have more and more number of turns, of course, your sensor output voltage will be increased larger, right? So that is something is important, right? If a sensor output for one unit is not enough, then you think about how to come with a series of this multiple sensor and increase the sensor output. Of course, most of this kind of gas sensors or chemical sensor is highly depends on the temperature. So that in this case, you see that for this particular sensor, you see optimize the temperature would be 300 degrees, then output signal would be highest. If you look at the Arduino's, the gas sensor, so that they always give you this kind of typical data sheet, right, to tell you about what's the typical here I show you in your Arduino kit. Usually they'll give you a typical reference the design, right, and they show you what's the typical current, and you need to make sure that the critical optimize the temperature operation to have best performance. Okay, so here, if you look at many of these commercial products, usually to give you some guideline to find the optimized design, right, operation of this gas sensor. Okay. Here I also show you in general why different catalysts may also have a different impact on the sensor performance. Here they show you that they have used different material, RU-PT and copper oxide, and so nickel oxide for different catalysts, and then they have impact on sensitivity and selectivity. Okay, so this is become very important. I think most of these kind of gas sensors or electrochemical sensor they actually highly depends on material. Okay, so you really have to find the optimized design the material to improve the performance of this gas sensor. Yeah. Well, here they show you one of a typical catalytic gas sensors respond as a function of input concentration of the gas. This is an alcohol. Okay, so again, typical gas sensor now it's only for the industrial application, for safety in industry, but also useful and important for the building or a smart home, right? So here they show you one of application of this kind of gas sensor for detection of the gas leakage made by a Japanese company. Okay, so, and of course, I think more and more companies that make more and more compact design of the gas sensor, right? In this particular model made by Yi-Kuen, they come with much more compact design and detect 6 gases. And you see, nowadays we have a more and more compact design now, right? Year 2000, this Yi-Kuen, they try to make the first watch time portable gas monitor, so that in the future, probably your smartphone or smart watches, you probably will find some of the not only typical man's motion sensor, probably also find this kind of additional gas sensor in your smartphone or smart watches. So I think it's very possible. And then if the cost becomes cheaper and cheaper, and power to run this kind of gas sensor is low enough, then I think it's possible that then you can have really more micro gas sensor for this kind of smart, not only smart building, but also smart watches, and also the smartphone can be used, right? Yeah. And so now we show you another family of this kind of a gas sensor. We call MOS. MOS means metal oxide semiconductor gas sensor. So in the beginning, Taguchi, right, in Figaro company, they come with this kind of MOS, metal oxide sensor, right? And then in 1968, and then in this case, this kind of MOS sensor allow to detect, I think, provide you have a low cost detection of a family of different gases and vapor, right? And then gradually, people also try to make this kind of electrochemical gas sensor. Okay, so this also common. And gradually in 1985, the city technology also developed this kind of oxygen and also electrochemical sensor, right, for detection of some toxic gas, and then so to some of the energy. So nowadays, including your Arduino kit, you do have this kind of NQ2 gas sensor. So basically, it's most commonly used this kind of semiconductor material is SNO2, the tin oxide. So basically, you have this kind of substrate, and then you have microelectrodes, your microheater, and then you deposit this kind of metal oxide semiconductor on top. And then in this case, if you apply the voltage, right, and heat up this metal oxide semiconductor to a certain temperature, in this case, you'll be more sensitive to some input gas. Yeah. And in general, this kind of MOS gas sensor has lower cost, but the selectivity has some limitation. So that in this case, you can think about how we can improve the performance. Of course, for smart building or building applications, you can see Honeywell had their IAQ, indoor air quality sensor. Yeah. So again, so this kind of basic principle of a metal oxide semiconductor gas sensor is, again, the idea is the absorption of gas molecule on this kind of metal oxide semiconductor. In this case, will produce the large change in this electrical resistance, right? And then if you can detect the resistant change, then you can use, right, to do this kind of gas sensing. So typically, what's the typical oxide used for this kind of MOS gas sensor is zinc oxide, tin oxide, and the other oxide. Okay. So there's another family of gas sensor. I'll show you the first one, the oldest one, is catalytic gas sensor, and then we have the semiconductor gas sensor. Now we have a number 3 type of gas sensor is electrochemical gas sensor. So typically, actually you use some special electrolyte. So it's in liquid form, and then you apply the voltage, right? And then there's additional some membrane. So if it's CO2, for example, you're doing CO2 gas sensing, right? The CO2, this kind of gas molecule diffuse to the sensor through the porous membrane. Okay, and then in this case, you will result in the output what? Change about electric current, right? In this case, if you can try to convert the change current into change of voltage, in this case, I can make this kind of electrochemical gas sensor. Typically, for this electric sensor is very much cheaper, but the problem of this kind of electric sensor is you have some drifting problem. After use it for a certain period of time, and then output signal will drifting. So here, let's look at more detailed design about this electrochemical gas sensor. Typically, you have this kind of the housing. And inside the housing, you have an electrolyte. It's like a water or some liquid buffer with some ion, right? And then you apply typically some operation amplifier, and then you try to have reference electrodes, and then you have counter electrode and this additional membrane. So then you let the gas molecule to diffuse into this electrolyte, right? In this case, if concentration reaches certain level, and then you can generate output signal, right? As so in this case, you can use this kind of electrochemical gas sensing. And here they show you more professional this kind of design of electrochemical gas sensor. Again, the key thing here is you have electrolyte, and then you have 3 electrodes, and plus additional temperature sensor. Why do you need temperature sensor? Well, temperature sensor is used what? As a temperature compensation, because many of the gas sensor or electric sensor is highly depends on the temperature, right? So this kind of temperature sensor actually used for temperature compensation of this kind of gas sensor. Okay, I think probably, I don't know if you have any question. We have already talked about for 1.5 hour. So do you have any question about our lecture up to now? Like a sensor, and I will give you watch this one special the ASME workshop about this kind of actually the speaker will come from all the industry, right? Engineer, and I think this is a very good way for you to learn from the real engineer in the industry. Yi-Kuen, Richard Payne is who developed the first ADX accelerometer.
Good morning. Welcome to ASME's
Professor Yi-Kuen was my teacher at UCLA.
Satellite broadcast. Sponsored by the Micromechanical Systems panel of ASME's Dynamic Systems and Control Division. Today's program is titled Microelectromechanical Systems, MEMS, Case Studies of Commercial Products. The program is televised from the ITV studio at the University of South Carolina in Columbia, South Carolina. My name is CJ Kim. I'm the chair of the ASME's Micromechanical Systems panel, and I'll be your moderator today. I'm a professor in the Mechanical and Aerospace Engineering Department of the University of California at Los Angeles, UCLA. I received my PhD in Mechanical Engineering from the University of California, Berkeley, with the study on MEMS. I joined UCLA in 1993 and have been teaching and doing research on MEMS since then. MEMS is an area attracting enormous interest throughout different disciplines in engineering and science, advancing with a tremendous speed these days. ASME televised a program on MEMS 4 years ago, introducing the technology. There are quite a few short courses offered in the States and other countries, as well as several formal courses and even degree programs in universities by a few, including myself. However, some of the common questions we have are, so what does this MEMS do? Or, that's great, but why don't I see the product in the market? Or, I have this great idea, how can I commercialize it? So today, we will try to answer some of these questions by showing examples. We have today 5 leading experts who will discuss not only the technology behind the products that have been developed, but also the economic advantages and limitations of using MEMS technologies from their own experience. Our presenters will describe the key MEMS devices that were successfully developed as commercial products, such as inkjet printers, airbag sensors, automobile fuel injectors, and pressure sensors. There are many products currently under development, but not hitting the market yet, due to the short history of the field of MEMS. I believe the commercial success of products like these today, in the meantime, will build confidence for further investments from both the government and the private sectors to sustain the growth of the field to the next level. This broadcast is live and interactive. We will have a question and answer period after each speaker, and also from 3:15 to 3:45 p.m. Eastern Time. We invite you to call or fax your questions in anytime during the broadcast. The toll-free number is 1-888-531-8685. I have to note that it is 888, not 8100, which is showing in your class note. The fax number is 803-777-6396. These numbers are also listed in your note. Again, the toll-free number is 888 and will be flashed on the screen periodically for your convenience. The number in your note is wrong. It is 888. There will be 2 breaks during the broadcast. 1 half-hour break from 12:35 to 1:05 p.m. Eastern Time, and a 10-minute break from 2:25 to 2:35 p.m. Eastern Time. 3 ASME videotapes will be played during these breaks for your information. During the first break, you will see Resource ASME and the Statue of Liberty. The other is Mothers of Invention, which will be played during the last 10-minute break. We also have a studio audience of local ASME members and other guests. I'd like to take this opportunity to welcome them, to invite them, and participate in the question and answer sessions. Our first speaker today is Dr. Richard S. Payne. Dr. Payne is the director of the MEMS Center at Analog Devices, Incorporated, Cambridge, Massachusetts site, where the first dedicated wafer fabrication line for surface micromachine devices has been built. He has worked for Analog Devices for 16 years and was at Bell Labs for 10 years before that. He's a fellow of the IEEE and the recipient of the prestigious 1992 J.J. Abrams Award. His presentation is titled, The Development of MEMS Airbag Sensors, which
Well, thank you, CJ, for inviting me here to talk about one of my favorite topics, that of the ADXL50. I'll give you a case history today that takes you through some of the motivations for the choices we made and some of the reasons why we made the choices we made, and maybe some of the economic factors and some of the developmental issues that we saw along the way. First, I'd probably like to tell you my definition, at least, of MEMS. MEMS are micro electromechanical systems, and coming from an electronics company to the ASME, I wanted to make sure you understood there were electronics in here too. I'll also stress the system aspect of MEMS quite a bit. They're typically involving a high degree of interaction with the real world. That is, they transduce signals from the real world, like mechanical, photonic, electronic, chemical, or fluidic signals or phenomena in the real world through a sensor of some sort into a core, which is really the intelligence of the MEMS system, a place where some signal processing or some control functions might be done on the signal. Following that, the signal would be transduced into some sort of actuation effect, in effect having an impact back on the real world. In some cases, in many cases, some of the early MEMS are purely electrical signals being generated to the outside world. In other cases, and some of the people that will discuss things later in the session, you'll see some fluidic and also other effects on the real world. When we initiated the development of the sensor back in the 1987-88 timeframe, there were several technology choices to be made. There are really various ways of implementing sensors and implementing microelectromechanical systems. In the first case, there was in existence a lot of devices made with bulk micromachining, that is, micromachining into the bulk of the silicon, and also some studies on surface micromachining. So we had to choose between bulk and surface micromachining. In terms of the construction of the device, one is also often faced with a question of whether to hybridize the system, build it out of several pieces, and make it a hybrid construction, or attempt to put everything on a single chip. And the third choice one often needs to make, and one needed to make in the case of a motion sensing device, one which could sense airbag crashes which necessitated the deployment of airbags, is the particulate transduction mechanism, whether one used piezoelectric or piezoresistive effects of the semiconductor device, or as was our choice, a capacitive sensing device. And I'm not sure you can see the colors terribly well, but at least the right-hand side shows things in green. The left-hand side shows things in red. It turns out part of my background that CJ didn't tell you about was that I went to Dartmouth College to get an undergraduate degree, and our color there is green, and our major rival is Harvard, whose color is crimson. So I always tend to use green for good and red for not so good. Looking at that first choice, that of surface versus bulk micromachining, the very nature of surface micromachining is that it's surface, as its name might indicate. It's made with standard integrated circuit technology on the surface of a silicon wafer, which is almost always the substrate in surface micromachining. There are really two critical levels in the process that are characteristic of the micromachining. First is a sensor layer, which I've labeled here in green, which is a polysilicon layer, and designed in our case to, and in most surface micromachining, to provide the active element, the moving part, or the actuator in a MEMS system. It's usually been placed in the process on top of a sacrificial layer, which in the latter part of the process is etched away to leave a freestanding structure as part of the overall system. In bulk micromachining, silicon substrate is typically etched through from the back in most devices, leaving some sort of membrane structure. What I should point out, and what really determined, one of the main reasons in our choosing surface micromachining is that the characteristic dimensions of the surface micromachine devices are in the neighborhood of 1 to 2 microns. We use a 1.6 micron sacrificial oxide and a 2 micron thick sensor polysilicon layer. So in that the characteristic dimensions are on the order of 2 microns. Very small structures, structures of that order can be made, although larger structures as well can be made. In the case of bulk micromachining, one of the characteristic dimensions is the thickness of a silicon substrate, and typically 500 microns on the order of 0.5 millimeter is the characteristic dimension. So if you want to make small devices and you want to make integrated devices, as was our intent, the choice of surface micromachining was fairly natural. The next technology choice that needed to be made in the development of this particular device was whether to use a monolithic construction as shown on the left, where the sensor and the electronics were fabricated at the same time on the same piece of silicon, or a construction in which the device was built out of pieces, a hybrid construction, where the electronics might be on structure on a second piece. Now, I think this is pretty much a case of choose your poison. I think there are pluses and minuses in both cases. In the case of our device, choosing a monolithic construction optimized the cost for us. In the case of some of our competitors in this field, the choice of a hybrid construction might optimize the choice for them. One of the things that's characteristic of sensors, and MEMS sensors are no different, is that some of the dominant costs end up in what I'll call the back end of the process, the assembly and testing of the sensor. They're different than integrated circuits, is one of the key differences, and hence the silicon costs are not in general the totally dominant cost element in the equation, and so you can live with, I would say, both kinds of constructions. And our choice, given the long-term system desires of the company and its business strategy, were to fabricate the device out of a monolithic construction. Well, having decided to essentially make a surface micromachine structure instead of a bulk structure, having also decided to use a monolithic construction as opposed to a hybrid construction, the choice of the particular sensing modality was very simple to make. In the case of silicon, there's really no viable piezoelectric effect. The piezoelectric effect in silicon is very small, and so to use a piezoelectric sensor in silicon would have amounted to introducing what I'd term a foreign material, something like PZT or zinc selenide or some other material that was not really compatible with the silicon processing, and especially not, which I'll get into a little bit later, not compatible with processing this material in a line in which many other integrated circuit devices were being manufactured. Another choice, and the one that had been made by the majority of people in the mid to late 80s when we started in this business, was the piezoresistive transduction mechanism. Piezoresistive effect in silicon was very well characterized and existed in many devices, but it has a characteristic temperature coefficient of resistors in silicon, which can be as large as 8,000 ppm per degree C. It is something which needs to be compensated for. So you start out with a transduction mechanism, which at the very beginning requires you to do some additional circuitry to compensate it. So what we chose was a capacitive transduction mechanism. Capacitor is inherently zero TC. First order, the dielectric constant of air or nitrogen, which is in most packages, varies by only 0.1% over 200 degrees C temperature range. So that the fact that there was no temperature dependence was a very strong motivating factor for us to choose a capacitive transduction mechanism. Another thing, being part of an integrated circuit company, was that we had a lot of good circuits, and measuring changes in capacitance turns out to be a particular circuit technique which is fairly easy and very powerful. So in the end, again, we decided to use a capacitive technique instead of any of the other transduction mechanisms. So in summary about the choices, there were really, the choice of surface micromachining enables very small sensors whose characteristic dimensions are in the order of a few microns. It enables monolithic construction. The process integrates much more naturally into a single chip construction. Surface micromachining also works very well for capacitive-based sensors. So again, it fit with that overall scheme of things for both sensors, and less so for actuators. But so far, the device I'll talk about, and most of the devices that I'll show you examples of during this talk, have very little other than electronic actuation, sending out an electronic signal. Certainly for the future, there's a high level of integration enabled by surface micromachining. And really, there are many paths to the future that this technology can enable. I'll try to show you a few of those paths as the talk unfolds. Since what CJ had asked for was a case history, I figured I'd give you the case history fairly explicitly. This project really began with a sensor that was in manufacture in the early 80s in analog devices, which did very well. It was an integrated circuit temperature sensor. And at that point in time, in a variety of different groups, a market research group in Europe and market research in the group that managed that sensor, they looked around for other things that might be done. So it was really a market-in project from the very beginning. Market-in being one where you ask the customers in the marketplace essentially what they want. By 1988, I became involved in the project, and it was formally, rather informally constituted. There were some other things that were formally started in 1988, but a group of people who were interested in trying to make an acceleration sensor got together. By 1989, those people had essentially abandoned what they were doing on other projects and became full-time involved in making an accelerometer, an airbag crash sensor. By 1990, in about a year, we had proven to ourselves that this whole project was feasible, but it took quite some time to develop a complete product and to convince several customers that it was worthwhile jumping to what was then a totally revolutionary technology. By 1991, early in 91, a very full function accelerometer, much like I think the picture I'll show you later has a mass date of 1991, and that was when the accelerometer itself was clearly demonstrated at the chip level. And at that point in time, giving something to sample customers, we developed 3 partners in the program, and we sampled parts to those programs in 91. And actually, in 1991 at Sensors Expo, we had a joint presentation with people from Berkeley that had been collaborators on our surface micromachining efforts, us having developed a component, and a systems manufacturer who had integrated it into a real product. It did take, 1992 is missing from this slide because it took a couple of years to really deal with all the issues associated with ramping from a feasibility demonstration, even though it was the final silicon, getting it into a package and required additional time. By 1993, it was in production on Saab 900s at a fairly modest level. The part was sampled to the world in mid-93. By 94, we had convinced the largest U.S. automotive manufacturer to use it on a select Buick, Oldsmobile, and Pontiacs. By 1995, an order of magnitude improvement had been realized, and by 1996, we see several million airbag crash sensors rapidly displacing mechanical components in cars around the world. Just a characteristic of the market that made this device especially attractive is that by 1994, there was nearly 100% penetration, shown in green, of mechanical airbag crash sensors into automobiles around the world. Either as a standard feature or an option, airbags are available on all 40 million automobiles. And the projection, given the fact that there's a significant cost savings going to a single point electronic accelerometer enabled system, is that by the year 2000, there would be a transition of these 40 million cars from mechanical switches to 60 to 70%, or 75% to 80% electronic, most of which we believe would be surface micro machine sensors, given the economics of the situation. So it was an excellent marketplace. And why is it that you actually need MEMS? Something we had to describe to our customers, and that is that motion is really required. You need a mechanical sensor. You need something more than electronics to make an airbag crash sensor. For our case, there was an IC line within the company. Analog Devices is at that point in time was about 500 million. There'll be $1.5 billion soon, and that was the environment in which and the constraints under which sort of we existed. And it was also a case that the circuit strengths within the company, the resources available to call upon, were there in terms of good, strong circuits capability within Analog Devices. So the very first system that we chose to implement was a very simple subset of that larger picture of MEMS that I showed. We like to refer to it as an acceleration to voltage converter. That is a system in which a monolithic chip transducts acceleration and outputs a simple voltage, which is proportional to acceleration, making it fairly simple for the user. Many of whom, in many of the systems applications that we were seeking besides airbag systems, are more mechanically oriented and want something that's very simple electronically. So we used a black box approach in the development in order to try to keep things simple. Quickly before I get into pictures of the accelerometer and the more complex system, I'd like to describe how the device really works. In this case, a polysilicon element is built with lateral capacitors, shown here with the proof mass displaced somewhat against these springs. This capacitor, which is smaller in distance, is actually larger in value. So this capacitance becomes, this differential capacitance becomes imbalanced, the one on the top larger than the one on the bottom. Into these fixed cantilevers are fed two equal and opposite electronic signals, 180 degrees out of phase. Those signals are then demodulated or amplified somewhat, and the phase, the phase of the larger capacitor comes out, and the amplitude due to the very small displacements is linear in displacement. So this is really a displacement transducer where the mass, a proof mass, is displaced against a spring and detected electronically. It's very, very sensitive. The displacement transduction of the airbag sensor is under an angstrom. It's about a half an angstrom that can be sensed. It's the equivalent displacement noise within the device. We built, again, a complete system on a chip. The block diagram is shown here, and I'll take you through some of these blocks to show you how the system actually works. The sensor is shown here, and I think I described that. There's a feature for the sensor which is self-test. Since it's capacitive with electrostatic capability, you can actually create motion with the voltages. So we can create an electrostatic self-test function that's on the sensor itself. There's an oscillator and a carrier generator that creates the signal I described on the last slide. It actually goes through a demodulator, a buffer amplifier, and there's a calibrated output at a place called VPR. That output is then fed to a final stage amplifier. That's the case because in the early days, we had 3 partners, and each of them wanted a slightly different range. So we reached an agreement where they could set the final gain. We would provide a calibrated signal, and they could deal with, amplify the output or filter it at this point as they saw fit. It also came with a standard reference building block such that the output was an absolute value of acceleration. They're shown here a block called feedback. In the first system, which I'll describe a little more fully, there's actually a closed balance force rebalance loop that essentially keeps the center member very close to its null point. The system was realized again in 1991 and shown here in the original package in which it was sold. Again, it's a complete monolithic chip. At the very center, you can see the exposed sensor, which I'll show you ever more close-up pictures of as we go on. It's in a 10-pin package, again, to accommodate the gain requirements of the variety of users. And it has something which you may or may not be able to see. It has trimmable thin film resistors. This whole chip can be calibrated at the wafer level. Looking at the block diagram a little bit, you can actually see the resistors that are trimmed a little more closely, and the fact that all of those functions described on the block diagram have actually been implemented on the chip. The sensor itself is I think very photogenic. It sort of made it into a lot of publications just because of its very colorful nature. These thin films are dielectrics on the order of a half wavelength of light, and they show that the tether, the sensor in actuality is 42 differential capacitance cells. Half of the proof mass is actually in the fingers that stick out, and half the proof mass in the center member. And again, this resides about 1.5 microns above the surface of the silicon. The very first device realized a sensitivity that was about 20 millivolts per G with about a 15% distribution, so that we could essentially sell everything. The distribution of sensitivity is about 1 millivolt per G standard deviation. The offset of the device is probably the hardest thing to control, and maybe I'll talk a little bit more about that later. The noise on the very first device, which has 10⁻⁷ grams of proof mass and a fairly sensitive circuit to detect very small displacements, is in the order of 10 millig's per root hertz. The noise in the device is very white. Excuse me. The noise in the device is purely white noise, so one can make trade-offs between several kilohertz of bandwidth and more noise, or a hertz of bandwidth and a lot lower noise. Well, from the beginning of the ADXL50, we went to several developments: customization of the package and the silicon, and also a rather dramatic improvement in the sensitivity. Finally, there was some architectural advances I'll talk about in a whole family of new devices, first spawned by a device called the ADXL76. The initial package, which was in a hermetic can, had the attributes that it's essentially welded. And so the properties of the device, which were established at room temperature in testing, were preserved very well through the process into the back end. But this device cannot be automatically assembled. Again, a feature that I'm sure many of the mechanical engineers in the audience can get involved in terms of integrated circuit automated assembly into PC boards. So Dept packages, in this case, an 8-pin through-hole mounted Dept, and soon to come a 14-pin 14-pin surface mount device were used for the packages. As I said, the improvements in terms of sensitivity and bandwidth were done through mostly improvements in the sensor. Some of you might have noticed that the original XL50 sensor was slightly offset. Excuse me. Was offset slightly from the center of the die. In order to, symmetry is often wise in doing stress-sensitive devices, which just about every small sensor is, multi-sensor. The device was placed in the center, and the electronics that was used is very much the same, with some minor changes. It's easier to see on the sensor itself the characteristic of some of those minor changes. Here you see a wider proof mass. This is a folded suspension which automatically stress relieves the polysilicon. And in some cases, we actually use the polysilicon as crossovers of some of the signals. So that, and the fact that the sensor was placed in the center of the die were some of the improvements. But in a force rebalanced architecture, you don't need all of the fingers to sense and all of the fingers to force. At 5G full scale, we separated force and sense, again, allowing a reduction in the noise and improvement of the overall system performance. So that in the end, we produced a next generation device, which has 200 millivolts per G, 10 times the sensitivity. The offset's more tightly distributed. The sensitivity is actually quite tighter. And the noise floor is down an order of magnitude to a millig per root hertz. So you can actually sense 1,000th of a degree or under a degree of tilt in it. Just a brief look at the actual material. You can actually see in this SEM photograph that the polysilicon material of 2 microns in thickness is indeed suspended above the substrate. And you're looking under one of these anchors. These are the anchors to the substrate. And there are very small stress gradients within the material, which you can see by looking at the ends of the fingers relative to the things that are fixed above the substrate. The next generation was really motivated in a very simple way by economics. The first generation device is XL75 shown here in this slide is 3 millimeters on the side. The XL76 has the dynamic range of the 75 and the 5 and is on exactly half the die area. Hence the silicon costs half as much. It has, again, many of the things learned from the 05. It has a much simpler electronic control system, enabling us to manufacture it at lower die area. It also happens to be a precursor of a CMOS architecture, which we will be using on the next generation process. This new architecture has spawned, and the surface micromachining technology capabilities have spawned a whole new family of devices shown on the next slide. It seems clear that since the sensor is on the surface, you can easily do a 2-axis device, and the 276 is a version of the 76, which actually has 2 sensors on the same die. It ends up being smaller than the original XL50 and offering a 2-axis for crash resolution, the direction of the crash. The 105 is actually something that has another factor of 3 of more sensitivity, range, and better specifications. 181 is a bomb fuse with integration of distance and velocity as well. 2 integrals done electronically on the chip. The 202 is designed specifically for tilting, measuring the tilt of platforms, especially toys and games. There's a single-axis version thereof. And the 310 is actually a microwatt accelerometer, which is all 3 axes measured on the same chip. So maybe getting into some of the summarization here. What we did in this is really a constraint-driven innovation, one in which you change very little from the IC line. You spend a little money. Actually, we spent very little in the first 3 or 4 years of developing the project to the point at which you really had feasibility. You create value for a customer and you get one that wants to buy it. Then you sell the process, and the process of optimization and really building a dedicated factory, which we're now engaged in, comes shortly on the heels if you're lucky. I might say that there's a philosophy, more or less, that I think is very important to recognize, and that's one of constraint-driven innovation. I was involved in the early days of CMOS when we were told by Intel that actually NMOS was the dominant technology and it would be forever. The short and sweet of it is they don't have that position anymore, but it was done, the development was done in a line without making any changes. Similarly, this MEMS development was done in an IC line without any changes and without any new equipment. It's a case to really sort of, if you want to do something innovative, but you actually want to get something done, it's good to live within the limitations and don't try to go too far until you've actually proven the point. I think that as we look forward, there are several things in surface micromachining that are important. I think we'll see CMOS being more important as a dominant signal processing technology. We certainly have a process in mind with multiple levels of polysilicon that build off what we know and yield very highly integrated microelectromechanical systems. Just as a quick overview, both visually, the next slide is a multi-project chip. We actually have MCNC signed up to broker this process in the next over the next year or two, wherein other people will be able to try this. But there are many functions that were demonstrated all on. This is on a single wafer and a single chip. For instance, accelerometers that can sense in all 3 directions. Angular accelerometers and resonant accelerometers with dynamic ranges of another couple of orders of magnitude. There are also angular rate sensors, which I didn't have a chance to talk about, but they're really exciting, which together with XYZ accelerometers should enable a 6 degree of freedom inertial measurement unit. There are also some signal processing elements that you can do on the chip. So finally, while we have a nice business going with a dedicated factory, there still remains quite a bit to do. I think in the area of MEMS, we're quite ahead of the game in terms of centers of excellence at Berkeley, UCLA, Caltech, Michigan, Case Western, CMU, MIT. There's several schools where people are actually getting to know about MEMS before MEMS pervade the industry, unlike the IC industry. But nevertheless, we need to develop a bigger manufacturing infrastructure, CAD infrastructure, some particulars associated with MEMS in terms of both materials and processing, as well as the whole packaging industry that now is geared to integrated circuits that we need to get geared to MEM. And finally, testing sensors is an area where there's an awful lot of work to do. So I guess with that challenge, I'll sort of open the floor to questions.
Thank you, Rich. Now we are ready for questions from viewers and live audiences. Do we have any incoming calls? I guess we'll start with live audience questions. Can you approach the microphone in front? Please identify yourself and your affiliation.
I'm Kathy Powell at the SMTC, and I'm a mechanical engineer. Why are MEMS accelerometers replacing inertial switches in airbag applications?
Okay, well, I think the pie chart I showed a fairly rapid, as automotive systems go, displacement of one technology by another. I think the real reason, and the reason that things happen in automotive, is cost. The mechanical switches, while in manufacture for some time, costs on the order of $8 to $15 per switch. Given the response time, they need to be located remotely in the car, and at least 3 mechanical switches, often more, were part of the typical airbag system. So you started out with about $50 to $75 worth of switches. They were located remotely, requiring connectors and wiring harnesses. Accelerometers are now under $5 item. They plug into the circuit board with a microcomputer, and just with an accelerometer and an inexpensive microcomputer, you can run an algorithm that determines what the energy in the crash and whether or not it's a crash which needs to be deployed. So it's also that kind of system. Electronic systems are also usable on multiple platforms. You don't need a customized configuration for every platform around. So the economics is on a good day, I claim that there's about $100 in cost savings on accelerometer-based systems over switch-based systems, and some people claim it's only in the $50 range. But $50 times 40 million cars is about $200 million, which people really want to save in the automotive industry.
We have an incoming phone call with questions. Go ahead.
Yes, Dr. Payne, this is Bonnie Love from Oak Ridge National Lab. And I'm asking about the current technology you're using for the assembly of these parts. What do you do for the assembly of these things?
Okay, the assembly of an integrated circuit is usually something where, in the first case, the devices are sawed with a diamond saw with a water spray. Needless to say, the sensitive structures on the front surface can't tolerate that. So what we do is essentially cover the surface with normal die mounting tape that has holes in it so they don't stick to the sensors. Then we cover the holes with another layer of tape. So we have two layers of tape and the wafer mounted upside down. That allows us to saw it. And then the pick and place equipment that's used in standard integrated circuit assembly typically has pins which move the device off a chuck and onto a substrate and back and forth from chuck to chuck in some cases. In those cases, needless to say, since we've located the sensor right in the middle of the die, that's where the pins are usually on those machines, we've substituted multi-pin handling systems that only touch the die out near the periphery of the die. So the die is essentially protected, sawed, and then dealt with with customized chucks such that the device is not destroyed in the process.
Okay, thank you.
Okay, we will have time to have another question from the live audience here. Please.
Okay, so I don't know if do you have any question for this particular talk. So again, this Richard Penn is the R&D I think manager who really developed the world first surface micro machines MEMS thermometer for airbag system in the car, like in any device company. So that I think his talk should be tell you about the real story, how he can really develop right from 0 to become 0 to 1, right? The real thing. So that is at this moment I told you all these kind of MEMS motion sensor for smartphones reach the $1 billion business, right? So that is something people have no idea, right? 20 years ago, but now it's really become the really big business. Beyond this smartphone or smart watches, and there's another big like a market now, right? Beyond smartphone. So I don't know, do you have any idea? Any big market for this kind of MEMS sensor? Huh? Another people think another huge opportunity for MEMS at least motion sensor is for VR, AR, or MR, right? In the future, we'll allow this kind of devices so that how we can use this kind of VR, MR for this smartphone, for this kind of new type of device is going to have very big, much bigger business now. Yeah, so that let me just quickly show you about this VR, AR application. I don't know if any of you have tried to play with a VR, AR game or some other application. Your smartphone, for example, the Google Map do have AR function, right? I think more and more smartphone app have this VR, AR function. Yeah. Let me show you about this interesting result about this. Yeah. So this is the one I tried to make a summary so that again, smartphone is rich saturation, but there's a lot new kind of a device, wearable device, AR, virtual reality like Facebook, Oculus. Facebook acquired this stock company Oculus for, do you know how much? I think remember about $2 billion acquired this stock company, and also you can see all the big company, Facebook, Samsung, Google, and then they try to develop this kind of VR and AR. See, this is become a bigger and bigger market. So that beyond, you see, of course, you see, you also need this kind of sensor, means a motion sensor. So that is something very important, right? And then, of course, you see, let me show you about all the product beyond smartphone, mobile VR device made by Samsung, Google, and the standalone Oculus, right? Vivo, Lenovo, and low-cost VR devices, high-end. This all need the MEMS sensor. Do you think how big is the market? And also smart glasses also needs a MEMS motion sensor. This is not small business. It's gotten bigger and bigger. Yeah. And so anyway, so here the people try to show this kind of the market. I just told you this MEMS motion sensor become bigger and bigger. And of course, in the future, you have IoT, right? IoT, this kind of application is another huge application, right? Yeah. Huh? Of course, for AR, VR, people also see there's another bit interesting is about this kind of video game. Why how use VR, AR for video game, so that the people find they should have another huge opportunity. Let me show you about this thing. This is the Lenovo, the product, so that they try to make some interesting video game. Lenovo's the AR. Also need a MEMS sensor. VR, AR, MR, mixed reality.
Your inner Jedi.
Well, I think this kind of video game is also huge market, so that all the big company, I'm pretty sure they will try to think about how to make this kind of VR, AR, or MR for this kind of application. Yeah. Anyway, so this is, I tell you, this is another huge market now. Yeah, yeah. Again, do you have any question for this particular part? I believe this is a MEMS undergo a bigger and bigger opportunity, because for this particular course, I expect I hope that you can learn about how to use commercial, this kind of sensor for some new application. That's why I hope that you can really do this kind of project to think about how to apply all kind of local sensor with Arduino to make an interesting project. Do you have any question about the project? Of course, if you need, I can give additional advice, right? So that any question about the project? Huh? You have no problem at all? One student asked about when should we give a presentation and report. Of course, originally we have make a original according to our syllabus. We do have the original schedule, but because we have this kind of disruption about this protest, and then so that we stop this kind of lecture for multiple times, so that of course I also want to ask you about your thing. This is original thing is that we will have this kind of final presentation in the final exam week. So do you have any concern about this original schedule, the day for the project presentation report? Original schedule here, but of course I understand we do have the problem, right? The university cancel. I think multiple lectures, and then so that do you have any concern? You think original schedule is okay, or you think you better to maybe delay for some period of time? This original schedule, right? Original project presentation schedule is here, is in the final exam week. Do you think you have problem, or you think you probably cannot finish the project and report, so you want to delay for one more week? It's okay. If I understand, so that I do need to consider about this kind of unexpected canceling of our multiple lectures. So that, how about, do you want to delay for one week? So that means, so if you are staying in Hong Kong, also one student asked about if you need to come to UST to a presentation or go through the Zoom. If you are still in Hong Kong, I I do hope that, and also there's no problem about transportation. HKUST is still come to UST for presentation and show your prototype. That will be better. If you are in out of Hong Kong or maybe in mainland China and you cannot come, then we can have a hybrid presentation. Do you understand? That's also possible. But it'll be better if you can come to UST to have this kind of presentation. Yeah. I don't know how many of you now in Hong Kong and how many of you not in Hong Kong. I want to ask the question. That's a quite important thing. Huh? Oh, most of you left Hong Kong. Oh, I see. But still some are in Hong Kong. But in this case, if possible, I hope you can come. But if you think very much more difficult, then we may come with hybrid presentation. Well, I hope that I hope you can come. You can come to AUT for this presentation and show the real working prototype. If it's very difficult, if it's difficult for you, we can also do the hybrid presentation. Means some of you some of you at USD and some via the Zoom.com. But anyway, I understand about this issue, so that in this case I will try to think about this thing. If it is difficult for you to come to Hong Kong, and then I hope that we can do some hybrid presentation for the project, right? I mean, for some of you can come to Hong Kong, and then you can do this kind of real presentation and show a prototype. And for those of you, you cannot come, and then you can also join this presentation through the Zoom. Huh? I hope that at least now we need to come with some more flexible way, right? So that some of you cannot come, it's fine, no problem. Try to we can do a presentation through a Zoom, because I think no problem. You can do presentation through this kind of hybrid mode. Yeah. Okay. Anyway, so if you still have some issue to need additional advice for your project, right? How to really make a better prototype, so that you can try to, I hope you can try to raise question on this our canvas, right? So I believe all of you can accept the canvas, right? So that it'll be, if you're questioning, and then most likely the other student also have question, right? So that if you can ask question now in this website, right, Canvas website, and then try to please ask question, right, in this Canvas, so that in the case I can let all the other students understand about the same question. And of course, I can also add additional reference now on our Canvas website, right, for some of the project. If you need additional advice or reference and or some device or programming about Arduino, I can also add additional information on our Canvas website. Okay. Okay. Any other question for the project? I understand this is unfortunately Hong Kong do have a problem, and then so that safety is the most important thing. I don't want you to have problem about safety issues, so that if you cannot come, it's fine. I understand. Yeah. Well, one student asked if it better to choose like all of you make a presentation video. Right? I think also interesting, right? So that as I show you about our previous years the project, so some of the team actually they can also make some video in their presentation, right? So that in this case, do you think maybe you try to make a work Arduino prototype, and then also try to make some video to introduce about your prototype, and then that would be interesting and useful, right? And then, some students ask me if you have some tutor time for the project. If you need some additional tutor time to give advice, it's okay. Please try to send me a message or try to email me, and then I can arrange additional like a Zoom video conference for your project. No problem. I can try to, we can additional separate rating for your project. Yeah. Okay, so anyway, so here I think I still want to continue about this SME workshop, right? Because I believe this is a practical. This presenter, they are really the pioneer, right, to make a real men's product. So that let's try to go back to our lecture, this video, and then so that I think this is quite useful for you to learn from the real engineer, right, who really make a real men's product. So that let's try to continue to watch this video. And then of course I will give you additional make some note for this particular thing. Yeah. Again, this you can look at this handout from our Canvas website. This video, the handout, is actually now in our Canvas website. Please download ASME handout.
Here from Charleston, South Carolina, mechanical engineer, basically. You mentioned that you had worked on a second chip that had 2 axes, X and Y, I assume. And then you mentioned that you had demonstrated that you could do 3 axes. I thought that was kind of strange. Could you explain on how you can get the 3rd axis when the wafers are pretty much layered? Okay, well, as you said, the 2-axis is fairly straightforward. Actually, the 2 different 2-axis devices that were shown on that family of proliferation family chart, one of them is actually 2 independent sensors, 2 mechanical elements, one rotated 90 degrees from the other. And that's the easy way, the straightforward way to do the second. And for some applications where you want redundant channels, it has a great merit. Simpler systems can be done with a single proof mass whose X and Y movement is monitored with X and Y capacitor plates. So one blob suspended off a spring with 2 degrees of freedom, and you measure the displacement of both X and Y. The 3-axis device is actually done with one sensor, which is a 2-axis sensor, and a second proof mass, which is actually a Z-axis capacitor sensor. It has a standard capacitor that's essentially not moving, and it measures the differential capacitance based on one plate that's free to move in the Z-axis and another plate and a fixed capacitance. So it's the same kind of differential capacitance circuitry. It's just a slightly different structure that moves up and down as opposed to laterally.
Thank you, Rich.
Thank you.
I think we just have one more question. I think we just have one more question coming in. Okay, go ahead.
Okay, hello. This is Nora Rogers, and I'm with Cordis Corporation. And my question is, back in, let me see, 1990, when you just started the feasibility for this program, how many resources did you have to accomplish the full functional accelerometer within a year?
Okay. Well, the project sort of started with 4 people. There were 2 senior engineers, a process and designer, and a junior engineer and a technician in the process group, actually. So the process development was the dominant activity in the early days, and it was 4 people. That expanded to a group of about 12 people by the time we demonstrated to ourselves that we were going to need to test and at both the wafer level and package. And right now there are about, it's hard to count them, but there are probably about 250 to 300 people spread out around the world involved in rapidly ramping to meet the volume requirements for this kind of device.
Okay, thank you really now this time. Okay. Our next presenter is Dr. James Jarramonte. Please move on. Dr. Jarramonte is a senior scientist in the Advanced Engineering Department of SSI Technology Incorporated in Janesville, Wisconsin. SSI Technologies is a supplier of sensors to the automotive industry. And his department is responsible for bringing new sensing technologies, preferably MEMS-based, into the automotive industry. Prior to joining SSI Technologies, he was an associate professor with the Institute for Manufacturing of Louisiana Tech University, where he was responsible for the design, installation, and startup of deep X-ray lithography equipment at the Center for Advanced Microstructures and Devices. He'll be speaking on the development of MEMS pressure sensors. Jim?
Thank you very much, CJ, for the very nice introduction, as well as inviting me to this talk. As CJ said, I will be describing the case history behind the development of a pressure sensor for the automotive market that my company embarked on back in 1989. And hopefully by the end of the talk, I will have described how this product came to be. So let me outline my talk for you. All right. I think for you as an audience, it'll be important to know a little bit about the company, because unlike some of the other companies represented here, our background and the way we got into MEMS is quite different, and that may be of interest because that also leads into some of the decisions that were made from a different perspective than the previous talk. However, you'll find that we ended up with almost the same conclusions. I'll talk a little bit about how our surface micromachine pressure sensor compares to micromachine pressure sensors, how we integrated that with CMOS currently. In other words, what is the fabrication sequence of that pressure sensor, as well as how we go about doing this without having the manpower that our previous speaker has at his disposal. In other words, we don't have a fab, but yet we can still produce wafers. Then we'll talk a little bit about the back end of the process, that is the packaging, as well as some of the current performance of the die itself, as well as the packaged die. So let me begin by describing a little bit about SSI. We are by far the smallest company represented in this talk today. We are about $90 million in sales per year. We mainly supply to the automotive market. There are a couple of markets that are side markets to us, but 98% or so of our businesses with the automotive sector. We're located in 2 places, Janesville, Wisconsin, where we produce our parts as well as perform the design. Then we have another office in Farmington Hills, Michigan, where we service our customers. And currently we have two product lines. One is a traditional sinter stainless steel components business. That is the origins of SSI, as a matter of fact. And we have the sensors business. Now, back in 1989, SSI, as it was moving toward the sensors business, looked at the automotive market to see what areas were being covered and what areas showed needs. And SSI came up with a list of possible applications where a pressure sensor could be used. This includes MAP and BAP sensors, that is manifold and barometric pressure sensors, oil pressure sensors, fuel rail pressure sensors. Brake assist was not there in 1989, but that is a new application mainly for the European market where they want to have brake by wire. Air conditioning systems, automated clutches, power steering, stored gas for some of the newer airbags where rather than using a detonating device, some people want to use a stored high pressure gas in order to activate the bag in a more gentle fashion. Turbo boost for some performance monitoring of the engine. And finally, tire pressure for both safety and run flat tires. So back in 1989, there were basically two types of pressure sensors being supplied to the automotive market in production. These were based on strain gauge technology and capacitive-based technology. Both of these are macro-based type sensors, that is, you can actually build these with your hands. You don't have to use photolithography to build these sensors. Both of these are still currently in use, although they are slowly being phased out in favor of some of the MEMS type sensors. At the same time, back in 1989, when SSI looked at the research being done in new sensor technology, it found that there was a lot of work being done in bulk micromachine pressure sensors, and there was some reported work on surface micromachine pressure sensors, mainly by the Lichtenberg group in Europe and Henry Ruckel's group in the United States.
So
the form are determined by carving out material from the bulk. This is usually done by some sort of chemical etching. I've borrowed here a schematic from Motorola to show how they package one of their bulk micromachine pressure sensors, as we do not have one. And you may not be able to see this in your in the screen right now, but in your notes you should be able to see that there inside of a package there is a pressure sensor mounted on a substrate, and the deflection of the membrane, which is on the top, determines the strain that is finally read off, and that strain determines what the output voltage will be of the, or the output voltage difference will be of the bridge. Now, incidentally, if I may stop here for a second and make an announcement, I was informed that there was a problem with the diskettes that were sent to ASME related to these transparencies. So some of you may have actually text and pictures missing from your notes. Those of you who have that can get the corrected versions from ASME headquarters in New York. I believe that the person to contact there is Ellen Lund. So if I may get back to my talk, this cartoon shows a finished bulk micromachine pressure sensing element, which was difficult to see in the previous transparency. And it basically shows that there is a cavity that can either be closed to provide a reference vacuum or pressure for the reading, a sensing membrane that deflects upon an external input, and on that membrane there are piezoresistors that read off the strain at the edges of the membrane as it deflects due to the external input. Now, in bulk micromachine pressure sensors, it is somewhat easy to also open up the substrate that is here in pink and create a differential pressure sensor. Now, our pressure sensor is a little different. It's based on surface micromachines, so let me walk you through that process. All right, in our process, we start out with an N-type silicon wafer, and we oxidize the entire surface of the wafer to be able to pattern openings. And usually after we put the oxide down, we put nitride and pattern the nitride to create the openings and create an oxidation that will define the cavity that we're going to use as a reference cavity. Then after we remove this oxide by etching, and usually this is some sort of a wet chemical H with HF, we regrow oxide. And for those of you who are not familiar with oxide, when oxide grows on silicon, it usually swells and it expands. So that as the oxide is regrown in this cavity that has been opened up, it will form this sort of geometry on the surface of the wafer. Following the regrowth of the oxide, we open anchors from the nitride and the oxide down to the substrate so that the polysilicon plate that we're going to deposit on top of that can have direct contact with the substrate. So we proceed by depositing the polysilicon and patterning the polysilicon. Once the polysilicon has been deposited, we can come back and etch out the oxide that is between the poly and the substrate. Again, HF etch shows a very high selectivity for oxide, so we can go in and clear that out without really impacting at all on the substrate and the poly that has been deposited on top. So we therefore now have a freestanding polysilicon plate that is suspended at the edges by the anchors that you see in this cartoon over here. Now, in order to seal the cavity and provide a reference vacuum, we can come back and oxidize the poly and the substrate together. As I said earlier, oxide swells when it is formed, and if it swells, it pinches off this cavity that was, or these channels that were used to etch out the oxide. And by pinching those channels off, we get a reactive seal. In other words, we can guarantee that there is no oxygen left as gas inside this cavity, and therefore we can, by some calculations, predict that the vacuum inside a cavity sealed reactively is roughly in the order of 10 to the minus 6 torr. Okay, so now that we've created our polysilicon plate and pinched off the entrance to the cavity, we can then come back now and put a dielectric film, a nitride film, between the polysilicon plate that we're going to use as a mechanical sensing element and the electrical polysilicon piezoresistor that we're going to use to read the strain from the plate. This is done by depositing a second polysilicon layer on top of the nitride, patterning the poly, and doping it appropriately so we can get the piezoresistive parameters that we want to get from those structures. Finally, to finish off the sensor, we make a contact to that piezoresistor by opening up a nitride coating that we put on top of the piezoresistor and providing metal to carry the signals from the piezos off to the rest of the die circuitry. In cartoon fashion, this is what our surface micromachine pressure sensor would look like. That is, we would only have one substrate, which is a silicon wafer we began with, the cavity defined by the oxidation steps, the polysilicon plate deposited on top of the oxide, and then the polysilicon piezoresistors that were deposited on top of the polysilicon plate. Now, what I have next are some scanning electron micrographs of some of the structures that I just described to you. And if you could zoom in, please, on the picture, I'll show you some of these structures that we just saw in cartoon fashion. What you see in this picture is the polysilicon plate.
Okay, I think, sorry, we almost run out of time. So I give you additional information for you to think about how to use this commercial low-cost pressure sensor, right? So that I told you, one of the pressure sensor which have been in mass production for smartphones, pressure sensor is STM. Okay, STM is one of almost the top two company to make this main sensor for smartphone. Right? If you try to find it's from Taobao, you can find this STM LPS 22HB. Okay, so that actually that is not too expensive. For one chip of this pressure sensor, it's about maybe 7 RMB. Okay, if you make a package this kind of pressure sensor for direct connect to Arduino, it's about 27 RMB. So that is not too expensive. Okay, so like a MEMS nano pressure sensor, so that you can try to again. I told you how to use this commercial sensor for real application. I think it's very practical. Let me show you this thing. You can easily try to buy this kind of sensor from this Taobao.com. Okay, so this is something I think should be very useful for you for this kind of application. So do you have any question for this? Unfortunately, I think we're almost run out of time today. So that but as it's important, I should give you additional information for your project and for this practical application, how to use commercially available sensor for real application. Do you have any question? For again, pressure sensor is one of very old main sensor, very mature, but still it still has a lot more application, right? So this kind of pressure sensor is not only useful for the barometric pressure sensor for your smartphone, right? You can also use what? Indoor location based service, right? Indoor navigation, right? When you go to the tall building and then if there's no GPS signal, and then actually you cannot, right? You cannot look at location, but it's quite important, right? So for some of these, if you want to do this kind of navigation in the very complicated building, and then so this barometric pressure sensor, I think still have their important application, right? So that is something I think is quite important, right? Let me show you for this kind of barometric pressure sensor in your smartphone, so that actually you can easily try to look the reading and pressure sensor. Of course, your smartphone also have all the motion sensor. If you can download the free app like Sensor Kinetics, so that you can read all this kind of motion sensor data from your smartphone motion sensor, accelerometer, gyroscope, magnetic sensor. Do you understand? So that that is, again, this is free. You can try to download free app from this, and then you can try to turn your smartphone into this kind of sensor system, right? So that this is Sensor Kinetics. Sensor Kinetic is free. Now the free app for smartphone, so that you can try to see. Let me show you. This is Sensor Kinetic. It's a free app made by a company, rotorview.com. Okay, so you can download this app, right? You can use for iPhone or Android phone, and then so that then your smartphone can give you all the data, sensor data, acceleration, also angular velocity, gyroscope, and magnetic compass, and many other things. So there's I think this is quite interesting. They have many different features. Okay. Okay. So do you have any question? So that we almost run out of time today. So any question for today's lecture or for your project? Huh? Any question? But anyway, try to download this free app so that try to enjoy your smartphone's main sensor, so that that is something is free, right? So that many of this kind of sensor, right, for smartphone so cheap, so that actually you can easily buy from Taobao. It is very so cheap. Yeah. Of course, most likely, if you have no experience, it probably difficult for you to use those kind of sensor chip, because most of this kind of smartphone sensor is a very small form factor, and the packaging is SMT, or SMT based device sensor chip. So it's very difficult for you unless you have very good skill, or you go to our UST lab, right, do some soldering, right, so that it's not easy for you to use this kind of sensor chip, right, main sensor chip for your project, right. But that's better. You try to buy those kind of a module, right, you know, from Taobao. So in this case, it's much easier for you to use this kind of thing for real Arduino project. Do you understand? Like, let me show you about those kind of packaged the sensor, right? You can buy from Taobao. Okay, let me check this thing. STM per sensor. This kind of pressure sensor. Okay, I try to find. You can look at this website, the Taobao, and then look at this absolute pressure sensor for smartphone. Yeah, and assuming you try to, if you want to buy, and then you try to get those kind of packaged sensor in a module, right? So you can easily connect to your Arduino. Yeah. Okay, I think we're out of time, so that I say for today's lectures, I will try to put this kind of today's video, right, and then on the Canvas website for those students who cannot join tonight's this kind of online lecture, so they still can watch this kind of video. Okay. Again, if a question, please you can try to ask question on our website, right? Our Canvas website, that will be much better for you, right? And then I can answer the question, and the other student can also learn. Okay. Okay. So I think that's it for today's lectures. So that okay, I think that's bye bye. Okay. Okay.